Hi everyone, this is Mr. Bowman, and in this video we are going to talk about some probability vocabulary. We're going to talk about some probability rules and a couple of ways to illustrate those concepts. So let's begin with problem number one. Suppose you are an observer standing at the bottom of a freeway off-ramp and you record the turning direction either left or right for each of the next three cars. One outcome within this sample space is LLR, which means first car turns left, second car turns left, third car turns right. A single outcome from a sample space is typically called a simple event. Part A, use the multiplication principle of counting to determine the number of outcomes in the sample space. So we have basically three simple events with two outcomes each. So 2 times 2 times 2. Or 2 to the third gives us 8 possible outcomes. List all the outcomes in the sample space. So you know you've got 8 outcomes, so we're going to be careful and try and be systematic about doing this. So LLL, LLR, LRL, RLL, and now we're going to look at the other possibilities. Right, 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 left, right, left, right, and left, right, right. And make sure you count that you have the correct number of possible outcomes. Moving on to the next page, I would like you to pause the video and write out the outcomes that define these events. Then unpause the video and check your answers. So these are the outcomes that define these three events. Take a look at those. Be sure to ask about any of those if you have any questions on them. Now we're going to introduce a little more vocabulary and notation. If we say C with a exponent, so to speak, of C, that means the complement of C or not C. So for example, event C defined up above is all cars turn in the same direction. So the complement of that is not all cars turn in the same direction. Most people don't use the English language that way, so another way of saying this is, or, I won't use or, at least one car turns in a different direction. I didn't want to use the word or there because that's used so much in probability. So C complement, not all cars turn in the same direction, one way of saying it. Another way of saying it is at least one car turns in a different direction. So what I would like you to do is I would like you to pause the video for a minute and determine the outcomes for A complement. So A complement means 0, 1, or 2 cars turn right, and the outcomes are shown right below that. When it comes to probability, the notation A union C or A or C implies all the outcomes that are in event A, in event C, or in both A and C. That is different than the English language. When we use or in the English language, it's an exclusive or. I'm either asleep or awake. When we use it in probability, we mean it's either event A or event C or both of those outcomes. So what I'd like you to do is pause the video, describe A or C, then find the outcomes of A or C. So A or C means exactly one car turns right, or all cars turn in the same direction, or both. And the 5 outcomes are shown below that. Now we talk about the notation B intersects C or B and C. And that means that those are only the outcomes that are in common to events B and C. Think of it as the intersection of two streets. 55th and Grant Streets is only where those two streets intersect each other. So pause the video and find or describe the meaning of B and C, and then list the outcomes. So if you said B and C is the same as all cars turning left, you are correct. If you'd like a little more practice, pause the video, do parts I and J, and then play the video and check your answers. If you said the union of any event and its complement is all the possible outcomes, you are correct. It's the whole sample space. The intersection in part J of A and C is the empty set because they have no outcomes in common. There's two ways you can note that. You can do brackets with nothing in it, or you can draw a 0 with a slash through it. Two events are called disjoint or mutually exclusive. Those are the same thing if their intersection is the empty set, if they have no outcomes in common. So the next thing we're going to do is we're going to represent the sample space and all the possible outcomes of the unions and the intersections of these events using a Venn diagram. These were discovered, or I don't know if that's the right word, but developed by a Dutch mathematician named John Venn. So what I'd like you to do is pause the video and fill in the Venn diagram using all the outcomes, the 8 possible outcomes from this example in the sample space, and then play the video and check your results. So these are the 8 possible outcomes that make up the sample space. So you should be able to verify that A has 3 possible outcomes, B has 4 possible outcomes, C has 2 possible outcomes, and outside of all of them are the 3 possible outcomes which make up the entire sample space. So to get a little practice with these Venn diagrams, we're going to do the first one together, and then I'd like you to pause the video and do the rest of them, and then hit play on the video and check your answers. So C complement would be everything outside of event C, and if we can shade everything outside of event C, then we can say, all right, all that shaded area represents the outcome of C complement. So pause the video and try the rest of these and then hit play to check your answers. Here are what your 3 answers should look like. To get a little more practice with this, I'd like you to do parts 3A and B. Pause the video, do parts 3A and B, and then hit play to check your answers. So you will see at the top A or B complement is equivalent to A complement and B complement. At the bottom, you'll see A and B complement is equivalent to A complement or B complement. That is not something you have to remember. Some of you who have taken computer science classes probably know this as De Morgan's law. The next thing we're going to talk about is probability models, and we use functions to represent them. So the domain of the probability function is the sample space, and the range is the probability of those outcomes in the sample space, which are going to be 0 to 1 inclusive. So in problem number 4, we're going to list out the sample space, and you recall the sample space are the 8 possible outcomes shown here. And in part B, it says, suppose that we let X represent the number of cars that turn right. The number of cars that turn right. Then the notation P of X means the following. The notation P of X means the probability that X cars turn right. And we can represent this probability model with a probability function. So the number of cars that can turn right are 0, 1, 2, or 3. And you can simply go to the sample space and count how many times that outcome occurs. So the probability of 0 cars turning right is 1 out of 8. The probability of 1 car turning right is 3 out of 8. The probability of 2 cars turning right is 3 out of 8. And the probability of 3 cars turning right is 1 out of 8. So a couple things you should notice is each probability is in the range from 0 to 1 inclusive, and the sum of the probabilities is going to be 1. At this point, what I would like you to do is pause the video, finish the rest of question 4, and do all of question 5, and then play the video to check your answers. Let's take a look at the solutions for the rest of question 4 and number 5. So here are the solutions for the rest of question number 4. I'll leave that there for a moment so you can take a look at that. You can even pause the video if you need to. If you have questions on any of these, make sure you ask about them. And question number 5, the sample space, the probability function, parts C and D, and E, F, G, and H. So even though you're probably familiar with these probability rules from previous math classes, I'm going to review them now. And the previous activities suggested these, that the probability of any event has to be a number from 0 to 1 inclusive. Could be 0, could be 1. The probability of any event or in the sample space occurring, or the probability of the sample space occurring is equal to 1. And the probability of the complement of an event is 1 minus the probability of the event. Furthermore, if we have two events that are disjoint, mutually exclusive, meaning A and B is equal to 0, we can say the probability of A or B is equal to the probability of A plus B. It's called the addition rule for disjoint events. It's based on the general addition rule. Lastly, you will see the A or B notation written as A union B. So the rest of this activity is really just using these ideas that you've experienced in the first part of this activity and getting some practice. So my suggestion is you pause the video, you work through as many or as few of these as you need to the point where you're comfortable with this, and then you hit play on the video to check your answers. So the sample space shown, the 36 possible outcomes for 2 dice, the sum of 2 dice, and this is showing that in a table, which I think is a great way to help illustrate that. The numbers that are filled in red are the sum of the 2 dice. And then events A and B are defined in part B, and here are the corresponding probabilities. As far as probabilities are concerned, my suggestion is, and what I want you to do, is to write them as unsimplified fractions. That way there's no chance of making a mistake, and also I can see how you were thinking about the number of successful outcomes or outcomes that define that event over the possible number of outcomes. And you can see that in all of these examples here, none except for 4 are simplified. Number 7, some examples with cards. Again, make sure you understand what events A and B are, how they're defined. A, drawing a 9 from a standard deck of cards, and B, drawing an ace from a standard deck of cards. Here's the Venn diagram that represents them. Remember, the Venn diagram, when you add up the probabilities in it, the total of the probabilities has to add up to 1 because it represents the entire sample space. So in number 8, a common mistake is for people to not know how to figure out the A and B, the intersection. And If two events are mutually exclusive, there is no overlap of those events, so A and B, or the probability of A and B, would be 0. In this case, event A drawing an ace and event B drawing a red card are not mutually exclusive. There are two aces that are red cards, so that's the 2 out of 52. In the other parts of the circles are the remaining outcomes in that situation or for that event. The general addition rule, which is shown here, adds the two probabilities, the probability of A plus the probability of B. So that's all of circle A and all of circle B. But you have to subtract off the A and the B because that portion in the middle, that 2 out of 52 in this case, would have been counted twice. So the next problem does a little bit of practice with this general addition rule. Again, I would suggest that you pause the video, work out problem number 9, and then hit play on the video and check your answers. So again, here's the general addition rule. That works all the time, regardless of whether or not the events are mutually exclusive. So we have these events defined here. This is our Venn diagram for that situation. Please take a moment, look at the Venn diagram carefully, because if your Venn diagram is incorrect, then the answers to the probabilities are going to be incorrect. And here's the answer for C. Again, don't simplify fractions. And then in part D, a variety of probabilities. Take a look at those, make sure you understand those, and also make sure that you can explain what they mean, because that may be a question that comes up on a quiz or a test or the AP exam. Letter E uses the complement rule. If I want to find the probability of a complement, I could take 1 minus the probability of that event. And the second part of E uses that De Morgan's law, if you want to think of it that way. So the Venn diagram can be represented with a two-way table, basically. And this is the two-way table that would correspond to that problem, the Sears Tower Wrigley Field problem, and the corresponding values that would go in there, which you would find in the Venn diagram as well. So you should be able to transition between the two of those. And here are the answers to the questions associated with that two-way table. Question 11, a little bit more practice. So if you want to pause the video, work out question 11, and then hit play to check your answers, you can do that. Here are the answers to question number 11. This is the Venn diagram for it. Show all of those to you at one time. And then finally, question number 12. If you want to pause the video, work that out, and then hit play to check your answers. Oops, sorry, forgot the rest of problem number 11 here. I'll leave that up there for a moment so you can check. And then finally, number 12. Showing that same situation using a two-way table. And the last question uses the general addition rule. And that is it for this activity. Make sure to ask your teacher if you have any questions.